All right. Well, happy Monday. Happy week 8. And yeah, time is ticking along. We've got just a little bit of time left in the quarter. So this is week 8. So we'll have lecture Monday, Wednesday, Friday. And then next week is week 9. And it's also Thanksgiving week. So I will lecture on Monday, and I'm going to just cancel Wednesday's class, okay? So we'll just have one lecture next week, okay? Monday, and then enjoy Wednesday off, enjoy your Thanksgiving holiday. And then after that is week 10. And week 10, we have our final exam on week 10 Friday, okay? And that will be it for this class. So as I'm thinking about it, we got today, Monday, Wednesday, Friday, week 9 Monday, week 10 Monday, 6 lectures, week 10 Wednesday, and then I probably don't want to cover anything new week 10 Wednesday. So really just 5 lectures of stuff that I would feel comfortable putting on the final exam. That week 10 Wednesday, I'll still have something, but I won't put week 10 Wednesday on the final. So anyway, that's what we're looking at. So yeah, the end of the quarter just kind of zips by pretty quickly. I hope your other classes are going okay. I imagine final projects and stuff, or I don't know, maybe yes. I'm always curious what you guys do in 101C, because that's often taught same time as this, and sometimes I do 101C in the summer, so I'm always just kind of wondering what's going on there. Okay, well anyway, today we are going to introduce multivariate stuff, okay? So we've been doing Markov chain Monte Carlo as a way to produce samples from a random distribution, a probability distribution. And so we saw, the Metropolis algorithm and Metropolis Hastings algorithm. And you've done that in your homework, or you're doing it in your homework right now. And I do want to say a couple things. So when you do your KS test on the Metropolis Hastings or Metropolis algorithm in your homework, if you have a pretty big sample, there's a good chance that it will look pretty good, like the ECDF will look pretty good, but not perfect, and your KS test might come in with a really tiny p-value. So there's a couple things you can do. One is you can just kind of play around with the seed, and you'll see how the ECDF varies from seed to seed. I recommend doing that anyway, just to get a sense of like how good or bad Markov chain Monte Carlo can be, okay? Part of the problem with Markov chain Monte Carlo is this autocorrelation, in that, every value that you get is based off of the previous value, and sometimes you repeat the previous value. That's part of the algorithm. And regular distributions, random distributions, don't repeat previous value. I mean, continuous distributions don't repeat previous values and things. So sometimes what people will do is we'll run maybe the Markov chain 2 or 3 times longer than necessary, and then just whittle it down, selecting only every third value or something like that, okay? And that way, you're just keeping kind of a subset, and you're 2 generations removed from the previous value that was kept. And so, less likely to have repeated values, less likely to have too much autocorrelation and things like that. So that's another way around it. But you can kind of play around with the seed, and as you do that, you'll get a sense of how MCMC, because it is kind of this random wandering chain, the results can can vary quite a bit. In the long run, if you let it run long enough, though, it will produce values from the stationary distribution. Okay, but anyway, let's get into today's topic, which will be transitioning into kind of multivariate applications. And I would say this is probably where MCMC really starts to shine, because for unidimensional cases, honestly, if you have the target PDF, then inverse CDF rejection sampling will probably get you will work well enough in most cases. But multivariate times is where we start to rely a little bit more on Markov chain versions of this. Okay, so here's kind of we'll just take what we know, the Metropolis algorithm, the Metropolis-Hastings algorithm, and just kind of expand it into a two-dimensional setting, okay? So the idea here is we have some target probability distribution, okay? A target PDF. Okay, target PDF, and this target PDF exists in two dimensions, okay? So here, I think I just have something that looks like a multivariate normal distribution. This is kind of a contour map. So, just imagine like a hill, or if you took the normal curve and then kind of, spun it around in a circle, you'd get a hill that's kind of perfectly symmetric. So just imagine spinning that around, getting a kind of a round hill, and then maybe stretching it in one direction, and you'll get something that looks kind of like a multivariate normal with some correlation between x1 and x2. Okay, so we have this target PDF. You don't need to have the exact form of the PDF. You can have a function f that is proportional to the target PDF, and that is good enough. So we'll just say we're working with some function f that is proportional. I mean, obviously, if you have the target PDF, that will work. But if you don't, you can get away with just using something that's proportional to it. Every observation now is a vector in two dimensions. Okay. So the Metropolis-Hastings algorithm or Metropolis algorithm works exactly in two dimensions or higher dimensions as it does in one dimension. Okay. In that you start at some arbitrary location. We're going to just call this x at time t, except now x is, a location x1 and x2. You are going to propose some new location, x proposed, and that is going to be, a location, again, in two dimensions. You have some kind of proposal distribution, and I'll talk about what could work as a proposal distribution. But yeah, let's say you start, down in this kind of corner here, and you'll propose some location from there, okay? And then you will calculate whether you should move to that proposed location or not. So you will calculate, if the proposed location is better than your current location, you will accept it, okay, with probability 1. And if not, you will calculate f proposed divided by f of x proposed divided by f of x current, okay? And if it's the Metropolis algorithm, and if this proposal distribution G is not symmetric, then you'll have to include this term, which kind of takes into account the fact that the proposal distribution is not symmetric. Okay, if it is symmetric, then this thing simplifies to 1, and it's just f of x proposed divided by f of x current, the Metropolis algorithm, which you're very familiar with because you had to do it on your exams and stuff. And then if it's not symmetric, then you kind of correct for the non-symmetric nature of G by doing X of, X current given X proposed divided by G of X proposed given X current, okay? You do that, so you calculate your P move, and then you will move there with that probability. So, if P move is 1, you definitely go there, and if it's not, then you go there with that probability. So you generate a random U value. If that random U is less than P move, you will accept it and move it, to that location. If it's, so the X at the next iteration, time T plus 1 is going to be your proposed value. And if it is not, then you will reject it. And then X at the next iteration will be your current value, X at time T. So it is exactly the same. All we've done basically is just turned X from a single value into a vector and a location in, a higher dimensional space. So it's the exact same algorithm. So here is one possible proposal distribution. You could do a uniform distribution in 2 dimensions. And the idea here is that you are centered at your current location, X at time T. X at time T, so this is, X1 at time T and X2 at time T. And then basically you propose, you go up or down some constant value in the X1 direction, and then you go up or down some constant value in the X2 direction. And so basically everything within this kind of rectangle has an equal probability of being generated, okay? So you will just, generate a new value somewhere in here. So you'll sample a new X1 value at the proposed location, X1 at the proposed location, and that will be a uniform value of your current X1 value, X1 at time T plus or minus C, and then you'll generate a new proposed value in the X2 direction, and that will be your current X2 at time T plus or minus K, right? And that's that. So any location inside this rectangle, equally likely to be proposed. Any location outside the rectangle has a 0 probability. And so your proposal PDF is basically the product of these 2 independent univariate PDFs. The PDF of going from plus or minus C is 1 over 2C, and then the product, the PDF of going to plus or minus K is going to be 1 over 2K. So the proposal PDF is going to be 1 over 4 CK, right? And C and K, you can use the same value. You don't have to use the same value, okay? And that is that. So that's how you can generate a value, and then you might, and so this would be symmetric, and you could just use the Metropolis algorithm there, okay? Another possible proposal would be a multivariate Gaussian, okay? Or multivariate normal. So you would be centered at your current location, X at time T, okay? Centered at your current location. And then you have some arbitrary variance covariance matrix sigma, okay? And it could be, you could have covariance, or you could leave the things independent, okay? If this, okay. And yeah, there is our library, multivariate normal library, that is able to generate random values from the multivariate normal. So you could just do RMV norm, and you just need one value because this is just a proposed location, and you give it your current location and some arbitrary value sigma, okay, and that will generate things like that. You can also kind of take this approach where you just generate an x1 and an x2 independent of each other, and you could just do our norm and just take your x1 direction, center it at x1 with some arbitrary variance value of sigma 1 or standard deviation sigma 1, and then you can take your current location in the x2 direction with some arbitrary value sigma 2, and then generate x1 and x2 independently, and that will be your proposed location. Okay. And again, if you do something like that, this will be symmetric as well. All right. So anyway, these are possible proposal distributions, and there are more that you could use, but probably multivariate normal proposal for something like this is probably fairly common, and that will work. Uniform also works, and that's how we would go about that. Okay, let me go ahead, give you your first few quiz answer, I think. What did I do? Okay, sorry. I thought I had it loaded. Okay, well, as I pull that up, one thing that can happen, though, with using the Metropolis or Metropolis-Hastings algorithm is that this starts to get rather inefficient in higher dimensions. So with 2 dimensions, it's okay. In 3 dimensions, it gets less better. In 4 dimensions, it gets even harder. Okay, so as the number of dimensions increase, the probability of a successful proposal will shrink. Okay, so let me just kind of illustrate. So when you have, let's say, a one-dimensional distribution. Okay, this is your target distribution. Okay, and let's say this is your current location, x at time t, and let's say we're going to use our proposal distribution is the uniform distribution. Okay, so we're going to basically go plus or minus some constant. Okay. And basically, if I propose in this direction, okay, if the value I propose goes in this direction, I'm going to accept 100% of the time, okay? But if I go in this direction, I'm less likely to accept, right? So let's just take it to the extreme, and then we'll just say accept versus not accept, okay? Right. So basically, I have about a 50% probability of falling on the kind of accept side and about a 50% probability of falling on the not accept side. Okay. Let's say I have a 2-dimensional distribution. Okay. And it looks something like this. And let's say I start over here. Okay, this is an exit time. So this is the area of higher probability. So if I generate anything in here, okay, I will kind of for sure accept. Okay, and then this is, I'm kind of moving away, right? So this will be kind of like the no accept. And then depending on kind of where I end up over here versus over here, okay, I may or may not accept. Okay, this is a little bit less uh, it's a little bit kind of wary over here, right? And so kind of the probability of kind of falling in kind of the high accept zone gets smaller, all right? So now kind of this almost for sure accepting drops down to 25%, okay? And then as it gets higher and higher, the number of dimensions goes higher and higher and higher, then it just gets, it gets harder and harder to get it correct, okay? So I guess you can, here's another way to think of this. Let's say you have this, so everything's kind of random, right? So you can think of like a random game where you're like spinning a wheel, okay, or spinning an arrow, okay? And we will say, if it falls in this zone, you will accept it. And then if it falls outside of the zone, you will not accept it, okay? Okay, so this will be kind of win, win, and lose, all right? So let's say right now you have around a 20% win. So this is just with one wheel, okay? And we can think of this as kind of like your x1 coordinate, all right? What if you have an x2 coordinate, okay? And then you have another wheel. And, you know, it doesn't even matter if this is anything less than 100%. So even if the wheel is kind of like this, where you have kind of an accept and a lose, like a win and a lose, okay? And you have to spin both wheels, the probability of getting both of them right is even lower, right? And then if you have another wheel, an x3, and it's kind of like, you know, if you go to Las Vegas and then there's a slot machine, okay? The slot machine that has like 7 wheels that you have to get like all in the correct thing is harder to win than the slot machine with only 3 wheels, right? And so, you know, as these numbers of things kind of get low, more and more and more, the probability that you're going to spin, you know, a good x1 coordinate and spin a good x2 coordinate and spin a good x3 coordinate, the probability that all of them are going to be kind of good coordinates is going to go down and down and down and down, right? So what happens is that you might have this proposal distribution, okay? And especially if your proposal distribution is, I'm going to just generate x1 independent of x2, and, or, you know, here we're generating x1 independent of x2 and things like that. The probability of generating a bunch of these things that all kind of work out and get accepted goes down and down and down and down, okay? And when you're in a high dimensional setting, generating these things independently just becomes not a great strategy, you know, especially if you're at like 10 dimensions, because the probability of, you know, then it really starts to feel like playing a slot machine with 10 wheels. And you're saying like, I sure hope I get the first coordinate right, and I hope the second coordinate. And because even if, let's say you generate not out of the 10 coordinates, let's say 9 of them are all pretty good, okay? But let's say that 10th coordinate that you generated is just like really, really, really bad, okay? I don't know. It's kind of like, have you ever had like a character creator on a video game, okay? And, you know, you can pick like the character's height and the character's, I don't know, like depending on, like you can customize all of these things, right? Like how long the arms are going to be and how big the hands are going to be and, you know, the size of the face and things like that. And I don't know, sometimes there's like a random button. And if you hit the random button, sometimes the resulting character just looks really kind of wild or almost grotesque, because if you generate a person's height completely independent of their arm length, completely independent of their leg length, you're going to get a person that looks kind of funny, because in real life, height, arm length, leg length are all kind of correlated, right? And so if you see somebody who's tall, we would expect their arms and their legs to correspondingly be also long, okay? But if you just randomly generated all three separately and independently, right? If you get somebody if you randomly generate a short height with long legs and long arms, okay, the individual will look a little out of proportion, okay? And basically, if you've got some kind of target, okay, where you have the region, is correlated or something like that, and you're generating each of these coordinates independently, okay? So you might get certain things. You generate x1, you get a decent thing. Generate x2, you get a decent thing. But if x3 or one of x10 is off, then the whole thing just kind of feels a little bit funny, okay? If one of these values that you generate is off, then the total kind of that entire coordinate just still doesn't quite feel right, and it won't get accepted. So what did I say, right? So I said, you might have some kind of thing where you're generating some value and you might accept only 10% of the values or something. So here I said, what if you just had to pick one random location along this line where only 1/10 of this location is kind of a high probability location? Okay, around 10% of the values that you propose would get accepted. If you do x1 and x2 independently, and let's say only 10% of the values in x1 get accepted and only 10% of the values in x2 get accepted, if you're generating x1 and x2, overall, only around 1% of those values will get accepted, okay? And as the number of dimensions increase, with 3 dimensions, only 1 in 1,000, in 4 dimensions, 1 in 10,000, and so basically, the proportion of values that you would have to generate starts to climb exponentially, and the number of values that you accept, or the proportion of values that you accept, shrink. Okay, all right. Now let me give you your view quiz answers. Let me give you your first two. And the first two are A and C. A as in apple, C as in cat. A and C. All right, so Metropolis Hastings will work, and you can do this. And so I know you guys are still finishing up homework 4. I will post one more homework 5, and that will be it. That will be your last homework. Homework 5 will be your last homework. And I'll make you do this multivariate Metropolis algorithm, Metropolis Hastings, and then also the Gibbs sampler, okay? So the Gibbs sampler is another kind of Markov chain Monte Carlo method that we have, but in contrast to the Metropolis Hastings algorithm, we reduce our problem down into basically a univariate problem, okay? So in Metropolis Hastings, you propose your next coordinate, okay? And so if your target distribution is a 17-dimensional distribution, then you have to propose a new location that exists in 17 dimensions, okay? So, it's kind of like spinning the slot machine with 17 spinning wheels, okay? And kind of, you have to get all 17 coordinates kind of just right in order to kind of win and get a good proposal location, okay? All right, and that's tough, okay? And I wrote, even if 16 of the coordinate 16 of the dimensions are in good locations, if one of the proposed coordinates ends up in a bad location of low probability, okay, let's say with a 1% chance of getting accepted, then the total probability of accepting that proposed location is going to be small. And then the probability of accepting that or moving to that location will be small. And the Metropolis-Hastings algorithm basically just is slow to generate good values, okay? Okay, do you remember, so last week we did this kind of deciphering thing, and I said, let's swap 2 letters, okay? Let's swap 2 letters, and if the swapping of the 2 letters ends up better, then we will accept it and go there, okay? And so when you swap 2 letters, sometimes it's better and you accept it, sometimes you swap them and it's not good, okay? Let's say instead of swapping 2 letters, I said, let's swap 10 letters, okay? Let's just take 10 random letters and kind of mix them up, okay? That new location that I'm proposing, will be wildly different, but I think we would agree it's going to be a lot harder to kind of find a better location, right? It's kind of like when we were at the very beginning where we just said, I'm going to just randomly shuffle all 26 letters, and here's another location where I'm randomly shuffling all 26 letters. Which one's better? And we might say like this one's better, but eventually finding like a good location is going to be tough, okay? And so kind of just by reducing it and taking tiny little steps, the algorithm works better, okay? So again, with Metropolis-Hastings or Metropolis, if your proposed locations basically takes into too much stuff, it's hard to kind of accept these things, okay? So with the Gibbs sampler, what we do is we are going to kind of factor out our multivariate distribution into a product of several univariate, maybe bivariate conditional distributions, okay? Now, this step could be challenging, right? The idea is you have a higher dimensional distribution and you're going to kind of factor it into a product of univariate conditional distributions. Okay, and so the idea here is, let's say your distribution, your target distribution exists in D dimensions, okay? What you're going to do is you're going to just generate one random value at a time, okay? You're going to generate, we're going to kind of factor this into a conditional distribution. We're going to say, what is the distribution of x1 if I hold all of the other values as constant, okay? So it's still a probability distribution, okay, but we're holding all of the other values constant, okay? Once I generate this x1, I'm going to hold that constant. We'll hold the other values constant, and we're going to generate x2, okay? And I generate x2. Then I'm going to plug in x1 and x2, the current kind of the latest values that I have. So currently this is, I have x in D dimensions at time t, and so I've got x2 at time t, x3 at time t, all the way up to xd at time t. And we're going to ask, what value should I use for x1 at time t plus 1? And once I get x1 at time t plus 1, I'm going to put that in. I'm going to put in my latest value of x1. And then, but I still only have the older values at time t for x3 up through xd, okay? But I generate x2. So I get x2 at time t plus 1. So now I have x1 and x2 at time t plus 1. X4 through xd is still at time t, but we use that to generate x3, and we so on and do that for every single value. Basically, whenever you want some value x at coordinate I, you're going to get the latest values at time t plus 1 for everything from 1 to I minus 1. And then for everything that comes after I, from I plus 1 to xd, you're going to use kind of the latest values that you have, which will be at time t. Did you guys cover coordinate descent in your 102A class? Okay, if you took it with me, we covered coordinate descent. If you didn't take it with me, I hope you covered coordinate descent. Okay, so in coordinate descent, it's an optimization algorithm where you basically hold one thing constant, or basically not one thing, you hold everything except one variable constant, and you optimize in that direction. Okay, and then once you get that thing, you move on to the next coordinate, and you hold everything else constant, and you optimize in that direction. This is kind of like that, except we're not optimizing, okay? We are generating a random value. So we say, all right, here's this multi-dimensional probability distribution. We're going to hold all of the other values constant, okay? We hold all of the other values constant, and this reduces it down to a unidimensional probability distribution. I'm going to now generate a random value from the unidimensional probability distribution. So the idea is kind of, so let's look at this in 2 dimensions, okay? So I'm not trying to, we're not optimizing, okay? So it looks very similar to what we did in coordinate descent. In coordinate descent, we said we're going to start at some location, okay? And then I'm going to hold it constant. And holding it constant, we say, okay, what does the function look like? And let's find the optimum in that thing, okay? Here, I'm going to hold. If I start here, okay, let's say I'm gonna hold x. If this is right, so this is x1, and this is in the x2 direction. Okay, I'm gonna hold x2 constant, right? And what I'm gonna get, all right, if this is a multivariate normal, whenever you hold one of these things constant, you get a normal distribution. Okay, so we have a normal distribution. Because what does this thing look like? It looks like I don't know. All right, so this is supposed to be some kind of 3-dimensional hill type of thing, okay? And the idea is if you slice it, okay, if you slice it down, a plane down in this thing, it's going to look like the normal distribution, okay? And what we do is from this normal distribution, we are not optimizing it, but we are just randomly sampling one value, okay? So I randomly sample a value, and so I might get something near the middle. I might get something a little high. I might get something a little bit low. Right? So here I'm going to just randomly sample one value in the x1 direction. And I said, okay, I sampled this one coordinate right here. Right? So by random sampling, let's say I select this value right here. Okay? So now I'm going to hold it constant in this direction. Okay? And if we look at what the normal distribution looks like when you hold it constant there, it might look something like this, or I drew it the other way. Okay. And if this is my random normal value, I'm going to just randomly select a location along here. Okay. So higher probabilities near the center where there's a high probability, lower probability out here, lower probability up there. So I don't know, maybe I select right here, okay? So I select my x1 coordinate and then my x2 coordinate, and then so this will be kind of my next location, right? And so this would be x at time t plus 1, okay? So I select this is my original location, this is x1 at time t and x2 at time t. Okay, this right here, this is kind of an intermediate location. This is x1 at time t plus 1. And this would be x2 at time t. Okay, and in here, now that I've got that, this is, x1 at time t plus 1 and x2 at time t plus 1. Okay. And then we go forward from there. So, so this will, so the advantage of this over, say, Metropolis Hastings is that it will get you to the target distribution area a lot faster. Okay, so let me see. I don't know. Okay, so we started, I don't know, like right around here, and then again, we're going to hold it constant here. And then, you randomly sample, so maybe we go right here, and then, you get something there, and you kind of keep going. Okay. Let me just contrast what Metropolis Hastings would look like. Okay. So, Metropolis algorithm, I said, hey, you could start at a terrible location, and it will eventually get you to the right place. And that is true. Okay. So, let's say this is our target distribution, okay? And so this is where everything is. We're going to start off at this terrible, terrible location, okay? Metropolis Hastings, I'm going to say, let's propose a random value from here, okay? And so, I might propose over there. We would reject it, okay? And then I might propose over here. And then, if I propose over here, I will accept it, okay? So I go here, and then I say now, okay, let's propose a new value centered at that location. And then maybe I propose down here, okay? And then so I move, okay? And then I propose a new value, okay, within a rectangle centered at that location. And if I propose over here, I don't accept, but maybe I propose up here or over here, and then so I will accept, okay? And so every time I do it, I take a small step, okay? And eventually, I will kind of get to my location that I should be at, okay? Notice with the Gibbs sampler, though, even if you start at a terrible location, right? So if you have your target distribution, okay, something like this, you can start at a terrible location, and if you hold this constant, right, along here, you might find, okay, the probability, univariate probability distribution is something over there, okay? And so the next value that you're going to get is going to be like somewhere over here, right? You're going to generate a random value, so it's going to kind of rocket you over here, all right? And then you look at this, and then you say, all right, well, what is the target distribution here? And then so after one iteration, because you select your x1, and then you select your x2 coordinate, after one iteration, you're kind of in your zone here. Right, so that's gonna, with the Gibbs sampler, if you are able to kind of factor it into these conditional probability distributions, the Gibbs sampler will get you to where you need to be a lot faster, okay? Whereas Metropolis Hastings will get you there, but because your kind of proposal thing, depending on what your proposal distribution looks like, it might take you a while to get there. Okay? And you might say, well, why don't I just make my proposal distribution even bigger? Okay? But again, you run into all of the same problems where if your proposal distribution is too wide, you're going to propose a lot of bad locations too, and you'll get stuck. Okay? So you kind of need like a smaller thing so they get accepted, but then you're taking kind of smaller steps, and it might take you a bunch of iterations to kind of get where you need to be going. Okay, Gibbs sampler, because you get the conditional distribution that you need, then when you generate a random value from this conditional distribution, it's gonna be from an area of higher probability. Okay, it's not gonna ever propose a value out here. Right. So the Gibbs sampler is gonna be much more efficient there. Okay. The hard part with the Gibbs sampler, though, is am I able to factor a multivariate distribution into univariate distributions, conditional distributions, okay? And sometimes, like if I said here's a multivariate distribution, if I hold it constant, what is the conditional distribution of x1? Okay, if I say, all right, so if I say if our target distribution is a normal distribution where the center is 3, 2, this is our mu, and we have sigma matrix equal to, I don't know, 2, 1, 1, 2, okay, so there's some covariance there. And I say, all right, let's hold x2 equal to be, I don't know, 2.5, okay? Then what is the distribution of x1 conditioned on x2 equal to 2.5? Right. What's the answer there? It's hard, right? Yeah, but this is what we need to be able to do. We got to say, okay, well, this is going to be a normal distribution where the mean, I don't know what the mean is going to be. What's the mean of x1 here? Okay, the mean of x1 is equal to some value, and then the standard deviation of x1 is equal to some value. I don't know, okay? So we got to be able to figure that out. So that's the hard part with the Gibbs sampler. But if you can do that, this is going to be much faster, much better, okay? So yeah, pros and cons to everything, okay? Metropolis Hastings, you don't actually have to do a lot of analytical thinking. You just need a function that's proportional to your target distribution, and then you just plug it in. Eventually it'll work, but not as efficient, okay? If you are able to do some of the analytical thinking to be able to factor the distribution, the multivariate distribution, into a series of conditional distributions, this is going to be better, okay? All right, so that's that. That's going to be kind of our introduction, or at least the motivation for why we're bringing up the Gibbs sampler in the first place, and then we'll get into how this works, okay? And so there's actually kind of a whole family of problems that lends itself really nicely to the Gibbs sampler, okay? And so we'll take a look at that on Wednesday. Okay, we'll wrap things up here. Let me give you your last view quiz answer. The letter D. D as in dog. D as in dog. All right, have a great rest of your day.